today. We've got a little bit of housekeeping kind of before we get going. Has everyone got a handout? I brought extras today. So I owe you guys an apology for telling you there were 3 weeks still in the semester. There's only actually 2. So you guys were quite right. I'm sorry about that. So this is the program for next week. We've got a lecture on Tuesday, your test on Thursday. And then on Friday, we'll go through the test, and it's likely we'll have a little bit of material still to cover. So we'll do a bit of lecture on Friday. Obviously, that material won't be in the test. It's okay. And then go through the test and just answer any questions and kind of wrap up my section of the course. Then I guess this is just to explain what's going on. So this is my baby, who is he's cute, but he doesn't sleep very well at night. Which means I don't sleep very well at night, which means my memory doesn't work quite like it should, which is why I convinced you all, or tried to convince you, that there was 3 weeks left of the semester. I really believe that. So, because we can blame the sky, we're not going to do a Vula quiz, because in my mind, we were doing this next Friday, so it's not going to work, because tomorrow's a holiday anyway. But what I've done is I've incorporated the quiz section in the test. And the good part about this is that in the exam, there is a quiz section. The first part of the exam is short answers. So you guys are getting practice doing this in the test, and we did the one quiz in class. So it's a little bit of a reorganization from what I told you at the beginning of the semester. And this is basically my fault, I'm sorry. Yes. Yes, so to clarify, the test is just my section. It's just the stuff you did with me. So stratigraphy, geological timescale, dating methods, and the geology of South Africa. Yeah. Yes. Yeah. And so, yeah, I'm sorry, but I mean, yeah, I guess it's no great loss. You don't have to spend the weekend doing a Vula quiz, and there's a quiz section in the test. So, I hope that's clarified everything, and I'm sorry, we can blame this guy. He's sweet, but he doesn't sleep. Okay, so there were lots of questions after the last lecture about this big, large-scale tectonic setting of the Cape Basin and then the Karoo Basin. And it's difficult for me to put this kind of in a nutshell to give to you guys. So this is the kind of textbook setting that we looked at, and this is what's happening, why we have the Cape supergroup, and we have this basin formed, and the whole system is under extension, which you get rifting, and this inland sea, which the Cape supergroup gets deposited into. But then there were lots of questions as that then the Karoo supergroup is a compressional setting, and you get the deformation of the Cape supergroup and these mountains. And lots of people were saying, but what the hell is going on? So the reason for this, and the reason it's difficult for me to give you a short explanation in the context of this course, I mean, we could spend 2 weeks talking about this, is this is what we looked at. And I said to you, between 700 and 500 million years ago, so for 2 million years ago, this is Gondwana land, and this is what's happening. But of course, this is like a massive oversimplification. In 200 million years, there's lots of dynamics, and there's stuff changing. And this South American plate is moving, there's dynamic things changing on this side. So to really unpick it and kind of go through and break down these big changes that's happening, we basically just don't have time. So I have to leave you with a kind of rather frustrating kind of oversimplification that this is the overall assembly of Gondwana land for 2 million years. And don't forget, this whole supercontinent had started down over the South Pole and moved itself. And during this time, there's dynamics which aren't kind of represented on a cartoon drawing like this. And that at the beginning of this Gondwanan time, the South American plate was a little bit further away. And in this area here, we have extension, and that's into which the Cape supergroup gets deposited. Yes? No, it's a very good question, because in the northern hemisphere, there was another supercontinent, which was called Pangaea. And lots of Asia didn't exist yet, because parts of it are much younger. But the cratons, which underlie kind of modern-day Russia and Asia, and North America, are all part of another supercontinent in the northern hemisphere called Pangaea. Good question. So then, in the early phases of Gondwana, there's extension in this part of the continent, and we get the Cape supergroup. But then as time moves on and the South American plate keeps moving, and it's moving faster than the other plates, that's when we get the deformation on the edge of southern Africa, which forms the Cape Fold Belt Mountains, which were much higher. They were over 6 kilometers higher than they are today. And on the other side of those mountains, you have the basin in which we get the Karoo supergroup. And another thing, which I told you incorrectly, someone asked me, we were talking about the Himalaya mountains, and I said it was the African plate. And someone said, isn't it India? And I was like, no, it's the African plate. So I was wrong. It is India and the Indian plate. So this is what I've been talking about. Then looking at the Karoo supergroup, where we've got a compressional setting. And it's to do with the South American plate moving, and we're getting subduction and the deformation and formation of the Cape Fold Mountains, and then the Karoo Basin is this back arc basin on the back of these mountains. So I realize it's a little bit frustrating to be left with this kind of simplistic overview, but for the time we have and basically the depth which you guys need to know this, that's enough. And I'm glad that you were interested enough to be like, what's going on? This doesn't totally make sense at this level. So today we're going to continue working through the Karoo supergroup. So we looked at the Dwaika, which is the basal-most rock unit, which were those special rocks formed by glaciers, and that's because all of Gondwana was down at the South Pole. Then we looked at the Eka, which are the deltaic deposits, so from big river deltas where it was very swampy and there was a lot of vegetation and we get coal. Then today we're going to look at the Beaufort group. So this is the next layer up in the Karoo. And the Beaufort group is characterized by braided to meandering river deposits. So you've got these enormous rivers, like the sides of the Amazon, basically. And you've got kind of large plains and these enormous rivers kind of meandering their way along. And they deposit incredible sandstones. So this is a photograph in South Africa, a road cutting, and you can see this huge, the cuttings exposing these beautiful sandstone layers that have been deposited by a braided or meandering river. And the age of the Beaufort group is a very important age in geological time. It's from the mid-Permian to the early Triassic. And so the Permian-Triassic boundary, where we move from the Permian era to the Triassic, is recorded in the Beaufort rocks. And it's probably the best terrestrial record, so land record, anywhere in the world. And there's an enormous mass extinction event at the end of the Permian, and which is best recorded in South Africa. So we're going to look at that as well. So if we looked at these various reconstructions of what's happening in the Karoo Basin. So this is the reconstruction for the Beaufort times. So during the Eka times, we had a very deep basin, and we had those deep marine sediments, and then we had those big deltas building out into this deep setting. So in the Beaufort times, this basin has been filled up, and basically there would have been a shallow lake in the middle of the basin. And we've got these high Cape Fold mountains to the south, and these enormous rivers coming off the mountains. And we know that the climate was wetter than today, and there was a lot of rainfall in the mountains, which then fed these enormous rivers, which flowed through into the shallow lake. So I guess this is just another way of looking at the same thing. So this is if you've cut a slice through the Karoo Basin. So here's our basement, which is in places the folded Cape Mountains, those mobile belts, or the Kafal Kraton, depending where you are in the basin. We've got the Dwaika underneath, the glacial deposits. Here's the Eka, and then we've got the Beaufort depositing. So you get these sandy deposits, and that's from the actual rivers. And then on the sides of the rivers, the overbank areas, you have muddier deposits, silt and mud, and that's deposited kind of on the banks of the rivers. And this is what we see all the way through the Beaufort group. And it was basically a very nice environment, and there's a very rich paleontology preserved in the Beaufort rocks. So this is just another look at the field photograph that I showed you, where you can see these sandstone layers deposited of the Beaufort group. So if you do a road trip from Cape Town to Joburg, you'll spend a long time driving through the Beaufort. So Beaufort rocks are really famous for their record of mammal-like reptiles, these primitive creatures that were not totally reptiles and not mammals yet. So the very important animals in evolution. And the major extinction event at the end of the Permian is very well recorded in the Beaufort. So this is a graph looking at extinction events. And this is the geological timescale along the bottom here. So we just have the pre-Cambrian. So they've just lumped all the Archaea and the Proterozoic. It's just called the pre-Cambrian. And then we start for real kind of in the Cambrian, where we have the Cambrian explosion, and here's the Cambrian fauna. And this is just going along through geological time, but focusing really on the later periods. And then on the y-axis, we're looking at the number of families. So this is a measure of biodiversity of life on Earth. And then we have, in the different colors, are the kind of different types of, it's basically dividing up the different types of life on Earth. But what we're looking at is just kind of an overall graph in yellow. And where we have these big troughs, that's where we have a major extinction event, where a lot of different families of animals have become extinct and died out. So the biggest and most catastrophic one is here. And this is as we go from the Permian into the Triassic. So this Permo-Triassic mass extinction event is, scientists seriously call it the mother of all mass extinctions. That's its official name. And it's very well recorded in the South African rocks. So I have a short clip of a much longer, like an hour-long documentary about this. And we're just going to look at a short piece of it that focuses on South Africa. So to look out for in this, they're going to show you some more Beaufort rocks in the field. They interview Professor Roger Smith, who's at the Iziko Museum here in Cape Town. There's a very nice reconstruction of what the Karoo Basin would have looked like 250 million years ago, and you'll see some mammal-like reptiles running around. And then it talks about the end Permian mass extinction event.
Quick question. Do you have a link to...
I think it's in the notes. Turn the page. My link isn't working. No, come on. Okay, the link into PowerPoint isn't working. I'm just going to play it by itself, and we're not going to watch the whole thing. We just have to skip ahead a bit. Okay.
Every living thing faced extinction. It's a period in prehistory called the Permian, when the Earth faced the biggest species on the planet. It was Earth's darkest hour. Scientists like Roger Smith.
The end of the extinction was as dramatic as a mass extinction could be since the beginning of life on Earth. There has been no other one that has come close to the 95% of species on Earth, both in land and sea, disappearing within a very short space of time.
It was the worst extinction. But without we wouldn't exist.
Had it not been for those few survivors, like tropical season. But 2 years ago, this would have looked a very different place. Rainfall in mountain areas were feeding Mississippi-sized rivers which meandered themselves slowly across the plains. This was a fully developed dictadons thrive. Huge herds grazed on the plains. But this plain is also home to a vicious killer. Years before T-Rex, Gorgonopsids was the Earth's most teeth. This were doomed. The mass extinction. And it was so devastating, so total, life itself was nearly wiped out. Its cause would be a mystery. Very place. Under this roof, paleontologists have unearthed rocks from this. My job as a geologist and a paleontologist is to read the rocks and to understand how they were laid down and to understand what happened to life ages. Now, sedimentary rocks like this are representing a point in time when position was taking place. The oldest layers are at the bottom and the youngest layers at the top.
So the principle of stratigraphy.
These rocks are like a time machine, taking us back 250 million years. He reaches the layer that records the moment the Permian world was wiped out.
Here we're sitting at the very top of the Permian, and this particular interval shows bluish grey rocks that clearly suggest that the environment was wet.
These rocks testify to the near death of our planet. The great green rocks were formed by the Earth, and they're littered with fossils. They tell us that this part of the world was once wet, lush, and full. But just above this layer is a very different story.
Suddenly everything turns red, and that's the labeling is the indication of drying, rapid drying and warming.
These red rocks reveal a sudden and dramatic rise in temperature and mark the point in time when life on Earth very nearly came to an end.
Fossils tell us at this point there is virtually nothing left on Earth, and we're going to
Changed. Below the line, grey rocks were fossils, life, above, red rocks, nothing. Life ceased to exist. And not just here. The dead zone was a line of death that travelled all around the world and could be found.
Okay, so the documentary, it's very good, but it goes on and on for almost another hour. So we're not going to sit and watch that now. But it's very good. They do a good job. So this is, in a nutshell, what happened. So this end Permian mass extinction event, and I'm afraid this slide isn't in your handout, but I'll put it on ruler. So this was the most severe extinction event in the history of life. and 96% of marine species, so all the life in the sea, was wiped out, and over 70% of all the life on Earth. And looking at places like the Karoo, looking at the rocks, it took 10 million years for life to recover the biodiversity that was around before the extinction event. So that's a really long time in kind of biological time, 10 million years. And what caused so this mass extinction event was recognized, but then what had caused it has been a subject of a lot of research and a lot of debate among geologists and paleontologists. But the most widely accepted and most probable explanation are massive, massive, massive volcanic eruptions, which continued for tens of thousands of years, and you get this enormous outpouring of volcanic lava. And this causes a run, which then adds a huge amount of CO2 to the atmosphere as well, and you get a runaway greenhouse effect. And you get massive, basically, global warming. Temperatures on land increased up to 10 degrees, which is enormous. And so on land, there was a massive, terrible drought. And in the oceans warmed up, and part of this warming of the oceans caused a release of methane into the sea. That methane clathrates, which are these molecules in the deep ocean, which store a lot of methane, were disassociated and released, which then released a huge amount of methane, which adds to this greenhouse effect and also causes ocean anoxia, that the oceans become anoxic, which basically just kills everything. Yes. Yes. Because of the huge amount of CO2 that was added into the atmosphere from the eruptions, yeah.
Volcanoes erupting too much.
Yes. And that there's this runaway warming then. It just, you put so much CO2 in that you get massive global warming basically. And then the feedbacks from that are things like the methane dissociates, and then you add more greenhouse gases, and it just kind of continues. It took 10 million years for the Earth to recover. So, and we see geological evidence of this in Siberia and in India at 250 million years ago, are enormous outpourings of lava. So the Siberian traps is what they're called, and the Deccan traps in India. And they're these meters and meters thick deposits of volcanic lava, which is the result from these enormous volcanoes. Question? No, I know the colors aren't great. So below the boundary, the rocks are green and grey. They're a kind of greeny grey color. And that's showing that it was oxidating, and it was wet, and there was lots of life, and there's lots of fossils in that. And then directly above those rocks, in that red zone, that's the death zone, where there's nothing alive. And that's the basin recording, because we don't have the volcanic event in South Africa, but we see the effect of this basically extreme global warming formed from the volcanic eruptions. Okay guys, let's not chit-chat. Can save that for lunchtime, huh? So, moving out of the Beaufort group into the last group that makes up the Karoo supergroup. So this is another simplified geological map of South Africa, where in the solid grey you have the Dwyker and the Eka, which have been lumped together. Then the Beaufort is in the spots and the stripes. So this is the different subgroups of the Beaufort group. And it's towards the top of the Beaufort group that we have the Permo-Triassic mass extinction recorded. And then above the Beaufort group we have the Stormberg group, and the Stormberg is in this dark grey. And then on top of the Stormberg we have the Drakensberg group. So we're going to look at first the Stormberg and then the Drakensberg. So, as I keep saying, if you drive across South Africa, you spend a long time in the Beaufort. Okay, so looking at the Stormberg. So the Stormberg age is late Triassic to early Jurassic, and this is really the age of the dinosaurs. So following that Permo-Triassic mass extinction, the dinosaurs are one of the groups that did very well in when you've wiped out almost everything on Earth. In the recovery fauna, the animals that flourished after that, the dinosaurs were one of the most successful groups. And in South Africa, we have three formations that make up the Stormberg group. So there's the Multino, the Elliott, and the Clarence. And we see different depositional environments, so the basin looked different during each one of these times. So in the oldest, in the Multino is similar to the underlying Beaufort, where we have braided rivers which give us sandstone deposits. Then during the Elliott Formation, the rivers are different. They are slower, meandering rivers with more floodplains, and we see more mud rocks. And in these mud rocks of the Elliott Formation, there's incredible dinosaur footprints. So these are different trackways from South Africa, and this one's in Lesotho, where you have these incredible mud rocks of the Elliott, and they would have been the riverbanks, basically, where you have soft mud on a riverbank, and the dinosaurs would perhaps been going to drink in the river and then have walked along the muddy bank, and then this has been buried by other soft mud and they've preserved the footprints. And they're really incredible trackways, dinosaur trackways. And then, so that's in the Elliott Formation. And then in the Clarence Formation, which caps off the Stormberg group, we have a different environmental setting. We have Aeolian sandstones, and Aeolian means that they formed in a desert, so desert environment sandstones, with some ephemeral rivers. So these are rivers which don't flow all year round, so occasionally they have water in them. So we'll look in more detail at what's happening in the Clarence, because this is a big environmental change in the basin. So this is the interpretation for what's happening in the Clarence Formation. So our Karoo Basin, we've gone from having, deep water during the Eka to an inland lake during the Beaufort with these large rivers, and then in the early Stormberg, we have the same setting where we have large braided rivers, and then by the Clarence Formation, the world is much drier, and we have a much drier signal, where we still have the Cape Fold Mountains to the south, but we have ephemeral rivers that don't flow all the time, so less rainfall, a drier climate, and we basically have the beginning of an enormous desert across southern Africa with these dunes, and these sand dunes, and this desert sand is what makes up the sandstones of the Clarence Formation. And this is what they look like in the field. So this is a photograph from the Golden Gate National Park, and this is what these cliffs of sandstone have this reddish color. There's very little bedding. They're these massive deposits. And if you go and look closely at them, they are Aeolian sand. So Aeolian is wind-deposited desert sand. And the grains are all very rounded and very uniform because they've been blown by the wind. So this is a much drier setting with these enormous sand dunes basically being preserved as sandstones in the Clarence Formation. And this is also, there's an incredible record of dinosaur fossils during this time, and this is a reconstruction of what this world would have looked like. There we have this desert environment with these massive sand dunes and then ephemeral rivers. So every now and again you would have some water flowing. You've got these small rivers. And the two quite famous southern African dinosaurs during this time, there's Massospondylus, which is the larger dinosaur, and Coelophysis, which was a small, it's a bit like the Velociraptor dinosaur, but a southern African one. So this is a kind of overview of what this Clarence world would have looked like. All right, and then the last group that we have in the Karoo supergroup, so the what caps off the whole of the basin, is the Drakensberg group. So this is a photograph of the Drakensberg in KwaZulu-Natal, and this, what we're looking at is you're looking up through the succession, and you can see these are the cliffs are the sandstones, and these are often the Clarence Formation sandstones. You can see them here. And then in between we still have some mud rocks, and then on top of this, the rocks that form the amphitheater and the escarpment, the Drakensberg escarpment, are the Drakensberg group. And this is a change in rock type, so all the way through the Karoo Basin we've had sedimentary rocks, but then the top, the Drakensberg group, are lavas. So they're basalt and rhyolite lava, but mainly basalt. And so at around 180 million years ago, there was this enormous outpouring of lava in South Africa, which forms and caps off the Karoo supergroup and forms the Drakensberg group. Yes. Next slide. And this basically ends the Karoo group sedimentation. So the Karoo group, we started with Gondwanaland down in the South Pole. We have the glacial deposits, and we move into a warmer world, and we have the rivers, eventually ending up with a desert, a very dry desert environment, and then it all ends off with this massive outpouring of lava, which caps off the whole basin. And the highlands in Lesotho today are all made of this Drakensberg group basalt. And then there's another aspect. So you get the basalt, which comes out at surface and forms the lava. Well, the lava comes out at surface and cools quite rapidly to form the basalt. But then you get the intrusive version of basalt, which is called dolerite. And this is a big thing in South Africa. And it's all links back to this time period of 180 million years ago. And the dolerite, so you get the lava extruding through the earth and trying to come out and flow out at surface, but you also get areas where it flows along fractures and faults in the earth and forms, and then would have cooled underground, and then it's formed dolerite. And the most common, we get dikes, which run and cut through the bedding, and then you get sills, which are bedding parallel. And they're a very common feature on the landscape of South Africa. And lots of these flat-topped koppies, like Roger Smith was talking about in the video, which again are a very common landscape feature. The top of these are these dolerite sills. And you can see here, these more resistant cliffs are the dolerite sills. And they are important. They're recognizable landscape features, and they're very important groundwater resources. Lots of the groundwater in the Karoo flows along the fractures which are related to where these sills are. So as engineers, it's something to remember and to look out for. And this is, it's all to do with the Drakensberg group dolerite sills. And we get the dolerite dikes basically all over that Karoo basin. And the reason for this, so where did the lavas come from? So what we believe is, we've zoomed into Gondwanaland. So we've got South Africa here, we've got South America here, the Falkland Plateau, which is this small plate that eventually moves very fast across the Atlantic to form the Falklands where they are today. And then in East Gondwana, we've got East Antarctica here, Madagascar up there. And Gondwana begins to break up at around 180 million years ago. And the reason for this is that a mantle plume begins to come up. So an enormous hot amount of molten magma from the mantle comes up kind of in the middle of Gondwanaland. And the plates on top just begin to basically rift and crack and be pushed apart by this enormous mantle plume coming up. And so the plume was probably around here. So this is kind of on the northern, this is the Limpopo. So this is kind of on the border today between South Africa and Zimbabwe. So we believe the plume came up somewhere there. And you get this rifting, and East Gondwana begins to split off from West Gondwana, which basically forms the modern coast of East Africa. And in the central part of South Africa, we have these lavas from this plume coming up on surface, which forms the Drakensberg, and the intrusive equivalents of that are the dolerite sills and dikes. So, yeah, I was waiting for the question.
Two questions at once. Doesn't this only have because I'm wondering what's the difference between this plume and a regular volcano?
It's a difference of scale. So a regular volcano is a kind of mini version of a plume. So this is, So I don't know. To go a step back at the mid-ocean ridge. So you're quite right. It's all the same mechanisms, but at the mid-ocean ridge, which is all underwater. So you've got the sea. This is all underwater. And you've got your convecting mantle that's bringing up molten lava from the mantle, and that's coming out on surface and cooling rapidly and building onto the crust. And it's because of this convection in the mantle that's pulling this crust apart along the mid-ocean ridge that's making space for the magma, the lava, to come up and form new basalt, ocean basalt. And we know because it cools underwater, it forms pillar basalts. And so this is what's happening at the mid-ocean ridge. But what's happening here is just basically a difference of scale that you've got. So if you look in a slice of the earth, this is a very bad slice of the earth, you've got the core and the mantle, and we've got a crust on top. And this is from the very deep part of the mantle that you get these enormous plumes coming up. And it's an enormous plume, and which brings a huge amount of hot molten rock up. And that's what begins to rift the surface and basically break open Gondwana land. And it begins to, this is the early phase of rifting of Gondwana, where you get a split between east and west. And we have the evidence of that in South Africa as the Drakensberg lavas. Is that
An example of intraplate volcanism.
spot on? And what's happening today in Hawaii, if you look at the Hawaiian Islands, so you have, it's called the Big Island, and then if you look across, you have all these, and that's the Hawaiian island chain. And what's happened there is that you have a plume, it's a smaller plume, but you have a plume that's bringing up lava, and that forms these massive underwater volcanoes. And what happened is that the plume is stationary, and the plate above it is moving quite fast.
Basically, essentially plumes. Also.
Yes, yeah, hotspots. Yeah, so if you look on the surface, it's kind of manifesting itself as a hotspot, and the hotspot is being driven by a mantle plume. And we see an example of that in Hawaii, but the Hawaiian one is relatively small compared to this one that broke up Gondwana. So, yes, question. Oh, yeah. Any other questions? Everyone all right? The breakup of Gondwana. So this process starts at around 180 million years ago, and we get this rifting and the Drakensberg lavas in South Africa. And it's a long process because the scale of this is kind of on geological timescales. So by 90 million years ago, so now we're fast forwarding 90 million years, and this is what it's starting to look like. So remember, at 180 years ago, we just had a rift here, but here we've opened up this rift. So this is the early mid-Atlantic ridge here, and we've got this early Atlantic Ocean opening up here. And South America is on its way to its present location. We've got this Falklands Plateau, which is this small piece of crust here, which is moving very fast and ends up down where the Falkland Islands are today in southern South America. We have East Antarctica moving off to where Antarctica is today. We have Madagascar, which stays more or less where it is. And during this phase, the opening of the Indian Ocean, it's when the Indian plate starts to move very fast and collides with the Asian plate and forms the Himalayas. And what happens in South Africa, so this Karoo Basin is capped off, and it's the end of Karoo sedimentation at 100 million years ago, 180 million years ago. And that's the end of the big South African rock record. So we started in the Archean, and we've worked all the way up to 180 million years. And if we look at a geological map of South Africa, that's all we really see. And the reason for this is this breakup of Gondwana, that South Africa becomes a stable continent. We don't have any more big basins. We don't have very much more happening in South Africa. But what we do have is that from this late breakup of Gondwana, we get this rifting across the southern part of South Africa. We also have some up here in KwaZulu-Natal. And it's in this rifting that we have some small basins filling in. Yes?
The movement of the Falkland Plateau.
Yes.
So quickly.
It's probably still to do with this massive plume that came up, and that's pushing this little plate. And this massive plume is actually still there. So if you look at the topography of South Africa around Cape Town and all around the coast is at sea level, but much of South Africa is actually very high altitude. I mean, Joburg is sitting at 1,600 meters above sea level, which is actually pretty high. And much of South Africa is if you look at the topography of South Africa, it's like a saucer turned upside down. So we have a narrow area around the coast at sea level, but most of South Africa is quite high. And the explanation for that is that that mantle plume is still sitting under Southern Africa and basically holding us up. There's lots of geophysical evidence for that.
Why does that? I mean, I understand why not.
Yeah, because of the Karpval craton. So the Karpval craton is this thick, old, cold crust that's basically just been popped up by the plume, but it's not going anywhere because it's tough, basically.
The drift, if it's the one that's next, if we say the whole crater, is it holding it or is it just lifting it up?
Today it's just lifting it up and it's just keeping it there. And this is a kind of a quiet plume now. But 180 million years ago it was hot and active, and it ripped right through the Karpval craton because the lava comes out. Okay, so this is like going back to 90 million years ago. This is zooming in to the last picture that I showed you. So what happens is that we have this Agulhas-Falkland fracture zone running along off the coast of South Africa with this Falkland plate moving very fast. And then so this is looking across, there's Durban, there's PE, Cape Town. So between PE and Cape Town, we have these faults in the Cape Fold Belt. And because of this, basically the plate moving, it causes rifting on this coastal platform and on the continent. And in these rifts, we get small basins opening and we get small deposits of rocks. And they're the Cenozoic, so it's our only record of the Cenozoic, the most recent geological record, is, as I said, up in KwaZulu-Natal, we have some record of a larger basin, but it's otherwise this small land basins, and then we have basins, the Outeniqua Basin, which today is underwater. Yeah, and we've run out of time. But if we just look at the geological map of South Africa, to kind of bring it all together. So this is all Karoo supergroup here, all of this, and the purple are these lavas. So this is the massive Drakensberg group. And then this bright yellow that you can see here, this is the Cenozoic record. So South Africa has a tiny record of the recent geological past, but we have this. So, and if you look on the geological timescale, it's that bright yellow is all of the Cenozoic, the last 65 million years. So the South African geology, the big stuff, is all the older things. So today's Thursday. So on Monday, we're going to look at the Cenozoic record, and then at kimberlites and diamond-bearing rocks, and then that really is it. So Tuesday. I really need more sleep. Okay, thanks, guys. Yes. Sorry?